Thank you very much. It's really a pleasure to be here in Zürich and to tell you about this field of attosecond science. So this is the outline of this talk. It will be a little bit historical talk. Where does it come from, attosecond pulses? So I will start by introducing to you the phenomenon of high-order harmonic generation. And then I will talk about attosecond light pulses. And that I will just say a few words about the physics that we do with these pulses. So nothing would have happened without the invention of the laser in 1960. This is a photograph of one of the first lasers, a ruby laser. And the invention of the laser, 1960, opened new fields of science. One of them is nonlinear optics, where you generate new frequencies by the interaction between laser light and matter. This is a second harmonic generation that was discovered by Peter Franken in 1961, so almost directly after the invention of the laser. And you have here this setup. The setup I'm going to show you are very, very similar. You start with a laser, you have a focusing element, focusing lens. This laser is focused into a piece of quartz. And then you have a prism here to analyze the radiation, and then a photon detector. And we're going to replace this piece of quartz with a gas of atoms. The other field that was open thanks to the invention of the laser is atoms in strong fields, very fundamental field, or multiphoton processes. Multiphoton processes were actually predicted theoretically by Maria Goppert-Mayer already in 1931. And here you have a two-photon excitation process where an atom is excited by absorbing two photons. In the 60s, Russian scientists studied multiphoton ionization of atoms by absorbing several photons. In 1979, Pierre Agostini and his group in France discovered the phenomenon of above-threshold ionization, where an atom can absorb more photons and be ionized, more photons than what is strictly needed for the ionization. And you can detect above-threshold ionization by looking at the electron's energy. So you need an electron spectrometer, and here, for example, you would see two peaks. My thesis work, which was at the beginning of the 80s, was about multiple ionization of atoms using multiphoton absorption. So here, for example, you have the double ionization of xenon atoms by absorption of many photons. At that point, it was clear that, okay, an atom interacts strongly with a laser field, and we can get multiplied charge ions, and we can also get excited atoms and ions. It would be very interesting to look at the fluorescence from these atoms or ions. So we set up an experiment where the goal was to look at the fluorescence from excited atoms or ions. So this is the scheme of this experiment. We have an intense laser pulse focused into a chamber where we have a gas of atoms, and we look with a grating and a detector. And this experiment was done at the Commissariat Énergie Atomique in the group of Gérard Mainfray and Claude Magnus. And this is a photograph of the laser that we used for this experiment. It was a neodymium YAG laser, 1 micrometer wavelength, 40 picosecond. And when you look at this picture, you see that, well, lasers have progressed. You see here the oscillator, and you have the two mirrors of the cavity here, and two amplifiers here. This is a picture of the setup. The laser is coming from the right. We wanted to look at fluorescence, and the fluorescence is emitted in all directions. So we had actually two detection axes, one perpendicular to the laser axis. So in here you have a grating, and this is the detector. And of course, one along the propagation axis. There is a grating here in this vacuum chamber, and then a detector. The lens is here, and somewhere here you have a gas jet. You can notice, now this is maybe for the older people here, it's also for the young people, we have a printer here. This is before computers. And we had a printer, and the pen was connected to the detector, and the grating was rotating, so we were following the motion of the grating and looking at the signal. It's doing this. What did we see? Well, we saw nothing perpendicular to the propagation axis. I'm not going to show you anything in this direction. We did not see much fluorescence, but what we saw is the generation of high-order harmonics of the laser field. And this is one of the first spectra. You see odd harmonics of the laser field. It's obtained in argon gas. You see that we are in the extreme ultraviolet region of the spectrum. These two peaks here might be fluorescence, I don't know. But what is very striking is we have strong high-order harmonics of the laser field up to 31st order, so very high orders. And if we plot the distribution of these harmonics on a log plot, intensities as a function of order, you see this very characteristic behavior with a decrease first, and then there is a plateau where all these harmonics have approximately the same intensity, and then a cutoff. And it was really unexpected and very fascinating. The reason why it was so unexpected, and this plateau behavior was really fascinating, because at that time we were thinking about nonlinear optics in terms of perturbation theory. I'm sure you have seen in textbook this kind of expansion where you expand the polarization in the medium in powers of the electric field of the laser. And for this expansion to be valid, you need the first order to be much stronger than the third, much stronger than the fifth, etc. And this was not the case. This is incompatible with this plateau behavior. You can also observe that we only have odd orders, and this is due to the symmetry of the interaction. It has a symmetry with respect to the origin, and this kills the even orders harmonics. So this was, again, a very fascinating result. And one thing that I liked very much is that it was a phenomenon that was in between the previous field I have introduced to you. It was both nonlinear optics, not in a crystal, but in a gas, and atomic physics, atom in a strong laser field. So this is how you can think of this single atom response. So every atom in this gas needs to generate high-order harmonics. And this can be described by the time-dependent Schrödinger equation, where you have here atomic potential, and this is the laser-atom interaction in the dipole approximation. You can consider this electric field to be classical. The difficulty is that this term is strong. It's comparable to the atomic potential. You cannot use perturbation theory to solve this equation. And actually, one of the first attempts to understand these high-order harmonics was to solve this numerically, this time-dependent Schrödinger equation by Ken Kullander. But there is also this second aspect, that it's a medium that emits these high harmonics, and in order to have efficient harmonic generation, you need that all of the atoms in the medium emit in phase. You need a certain phase matching condition to be realized. And this is described by Maxwell equation, which can be simplified to a wave equation, as you see here with a generated field that depends on the medium polarization. So this is one of the first calculations, solving the time-dependent Schrödinger equation performed by Ken Kullander, and Ken Kullander actually passed away just approximately 1 month ago. So it's kind of nice to talk about these results that were really important in our field. So what you see here is that, the calculation actually seemed to reproduce more or less the experimental result, which was also a surprise, because we thought that phase matching would be more difficult to realize for the very high orders relative to the low orders. And when you look at that, you think, oh, but actually it seemed that it works. So it was also important to solve both the Schrödinger equation and the Maxwell equation, the wave equation, which we did a couple of years afterwards, reproducing more or less the experimental behavior with a decrease and some kind of a plateau, and then the cutoff. Here you have results at different laser intensities. So now we can simulate the results and more or less reproduce them. Does it mean that we really understand them? No. So now I'm coming to a little bit laser. This field has been pushed and is still pushed by progress in laser technology. And now we are at the beginning of the 90s. There is really a huge progress in laser technology because of titanium sapphire. There's really, I think, 3 discoveries at the same time, approximately the same time. You have the chirp pulse amplification that led to Nobel Prize to Donna Strickland and Gérard Mourou in 2018. You have a new laser material, titanium sapphire, and then you have a new technique to generate short pulses from oscillators called Kerlens mode locking. And here you have 3 Swedish scientists looking at these 3 technology, and they actually decide to buy a laser system, putting together these 3 inventions and building the terawatt titanium sapphire laser at the Lund Laser Center. And this was going to be a kind of unique laser in Europe for a few years. And the titanium sapphire technology has been really the standard in our field of research during many, many years, and it still is very, very much. So there is, in parallel to that, there is also a progress in instrumentation. And in Saclay, we decided to build really dedicated instrumentation for studying high-order harmonic generation. And you have, so this is myself many years ago, and my first 2 PhD students in France, Philippe Balcou and Pascal Salière, is in the window here. And this is the instrument that we built with a gas jet here. So the laser is coming from a hole here. Optics to analyze the radiation, toroidal mirror and a grating, and then electron multiplier, which is used as a photon detector, which is here. This is also the time where computers appeared in the laboratory, and the first personal computer. And I remember spending a lot of time just programming an acquisition program to really to acquire data. And the first laser we used to test this instrument was actually a horrible laser. It was a neodymium glass laser using the chirp pulse amplification technique, 1 picosecond pulse duration, that was good, 1 shot per minute, that was terrible. This is the time where I was invited to come to Lund to try their fantastic new titanium sapphire laser. And of course, I came to Lund with this instrument and with my 2 PhD students. And we did the experiment with titanium sapphire, at that time 200 femtosecond pulse duration, 10 hertz repetition rate. And we could really use the new computer capabilities, and we could make use of this high repetition rate in taking data. This is one of the spectrum that we took at that time in helium. You see here a very nice plateau, starting actually much before, but here you see from harmonic 51 to harmonic 93, so we are really in the extreme ultraviolet range now. So I'm now coming to the second part of this talk, which is attosecond light pulse. The attosecond pulse idea came along, sorry, I'm mixing Swedish now, but came along actually very soon after the discovery of the high order harmonic plateau. Was kind of natural idea for people dealing with mod-locked lasers. And here's the idea, very simply, on this cartoon. So I'm plotting here 3 harmonics, 17, 19, 21. And let's assume that these 3 harmonics are phase-locked, which means that the maxima coincide at some time. Because of the periodicity of the process, the minima will coincide at half the laser period, and then again the maxima, etc. And if you add these 3 waves, you get a train of very short light pulses in the attosecond range, which means typically 100 of attosecond. And this was realized by a few scientists, as you see here. If you add not only 3 harmonics, but 10 harmonics, you can get even shorter pulse. So what is plotted here is the intensities of these attosecond pulses. So the advantage is that at that time there was really also enormous progress towards shorter and shorter laser pulses, towards few femtosecond, but there was some kind of barrier called the femtosecond barrier. It was impossible to go down below a few femtosecond using visible light, and the reason is of course, the frequency of the light. In order to have short pulses, you need to have short periods, so you need to have high frequency. And this was what these high harmonics had. We are in the extreme ultraviolet range, high frequency. You also need a broad bandwidth. The smallest pulse duration that you can get is inversely proportional to the bandwidth, to the inverse of the bandwidth. And again, this high harmonics plateau, this gives you a broad bandwidth. So the question was, are the harmonics phase-locked? And it was not a trivial question. We are going to take 14 years to really be able to answer this question. Myself, I was actually very skeptical at first. Now, I talked about progress in laser and in technology. There was also a huge progress in understanding in 1993 with what is called the 3-step model, which was proposed by Ken Kullander, Ken Schäfer, Paul Corkum, approximately at the same time, and Maciek Levenstein actually formulated this model, proposed a quantum formulation of this model called the strong field approximation that was going to have a very strong impact in this field. Now here you have a cartoon showing this 3-step model. It's a very nice, intuitive picture of the interaction. And what you see here is the atomic potential, which is deformed by the laser field, which is moving like this in the laser field. So at some time, you see that there is a potential barrier here. So the electron in the ground state has a certain probability to tunnel through the barrier. And then the electron is then driven away over a few nanometers. When the laser field changes sign, the electron is pushed back or may be pushed back towards the core. And then there is a certain probability for recombination. And in this process, you have emission of light. If you consider the different possible trajectories in this semi-classical interpretation, you can easily see that depending on the time of ionization, when the electron is released here, you can have different type of trajectories where the electron comes back with different energy, and also at slightly different time of return. So you can see here that you have a wave packet with a certain bandwidth, which is very large. This is the plateau. And also a certain duration, which is in the order of 100 attosecond. And this process is repeated twice per laser cycle on one side, and then the next half period on the other side, and again and again. So in the frequency domain, this will give you odd order harmonics. So suddenly we have a very nice intuitive picture of this process. There was also a progress in understanding of the second aspect of the problem, phase matching. And very simply, in order to achieve phase matching, you want that the phase velocity of the fundamental field propagating in the medium to be equal to the phase velocity of the harmonics. So you want this to be realized. Here I'm plotting a picture from this book by David Atwood, showing some kind of general behavior of the refractive index in materials as a function of frequency, and you have different absorption edge here. You see that in the region where the fundamental is, refractive index is larger than 1, while in this extreme ultraviolet region, the refractive index is less than 1. So this shows you, well, that it's impossible to achieve phase matching. Now, fortunately, at the same time that we have this harmonic generation process, you also have electrons that are created that never come back, that move like this away. So you get free electrons in the medium, you get partial ionization of the medium. And these free electrons are going to change the refractive index for the fundamental. So they're going to lower this refractive index here, not really affecting the one for the harmonics. So you add a negative contribution here, you achieve phase matching. And the degree of ionization that you need to achieve phase matching is typically a few %. So phase matching is actually clumping the phenomena. You cannot increase the intensity a lot because you're in phase matching. There is a really window where you get these processes. The intensity needs to be high enough for the generation of these high-order harmonics by each atom, but not too high in order for phase matching to be achieved. This is a little bit simple description. Let me just add here as a disclaimer here, it's a little bit more complicated than that because actually there are different regimes of phase matching. You can also use the influence of focusing, which you need. So you have a GUI phase varying in the medium, And this also plays a role. So in some regime of phase matching, you compensate this refractive index for the fundamental with help of this variation of the GUI phase. So progress in understanding, also progress in experiments. So now I'm moving to the end of the 90s. In 1998, we did an experiment in Lund. This is the time where I had moved to Lund. And we really wanted to study the coherence properties of the high harmonics. And we did that very simply by making two harmonic sources using, of course, from the same laser, using a mesoline Michelson interferometer. And then we look in the far field to see if these two sources interfere with each other. And we have a grating here somewhere to separate the different harmonics. And this is the result that we obtain for harmonic 15. I hope you see beautiful interferences that show that, yes, this is coherent, spatially coherent line. This experiment was performed by this group of people, and you have Mette Gordon. She was my first student in Sweden. She's from Denmark. And Ted Hensch, Marco Bellini from France was a European collaboration. In addition to these interferences, you see two different regions. There is a collimated part and then a more divergent part. And this was the signature of different electron trajectories contributing to harmonic generation. This was the first experimental confirmation of this three-step model. There are short trajectories where the electron is getting away and come back very quickly, and long trajectory where this excursion in the continuum is much longer. And if you consider the phase, now I'm a little bit technical here, the phase accumulated by the electron on its trajectory, in the case of a short trajectory, there's almost no phase accumulated, so it's divergent beam. While for long trajectory, you have a larger phase accumulated, and this phase depends on the point in the medium, so it depends on R, it depends on the intensity, the local intensity. So it leads to a curvature of the wavefront, which is why you get this much more divergent profile. So when you have this little bit different trajectories, you can also see that you can actually start to control them. And for example, you can aperture this profile and get only the short trajectory contribution, which Pierre Agostini was going to use in his experiment. So now I'm coming to we are at the end of the 90s. We think that, at least in some case, it's possible to get attosecond pulses, but we are not sure. And we need to measure this. And at that time, it was not clear how to measure attosecond pulse. The most common idea, this is something we tried to do in Lund without success, was to try to do an autocorrelation measurement. But this was very difficult because this process is not very efficient. The conversion efficiencies are of the order 10 to minus 6 or something like that. So it's very, very difficult to do two photon. It's still difficult today to do two photon process using harmonics. So fortunately, both Pierre Agostini and his group, and actually Fair and Cross, they used a cross-correlation experiment to measure attosecond pulse. So now I'm coming to the first measurement of attosecond pulse. And first of all, attosecond pulse in a train of pulse, which was realized by Pierre Agostini and his group in 2001. And this is really why he got the Nobel Prize for this very important experiment. So here is the idea of his measurement. So it's based on a theoretical idea by the group of Alfred Mackay, and using a two-photon process using a harmonic and a laser photons. So if you do this two-photon ionization process, you end up with a main peak here and a sideband peak. You can reach this sideband peak by another process where you have absorption of the next harmonic and then stimulated emission of a laser photon. And this technique was called rabbit, which means reconstruction of attosecond beating by interference of two-photon transition. So now we have two quantum paths leading to the same final state. So we add the amplitudes of these two paths. And adding the amplitude of these two paths, you get a signal that depends on the relative phases between the two paths. So let's look at these phases. Well, you have a phase which, this is the first quantum path here. You get the phase of harmonic Q. You have also a contribution from the ionization process, which I'm going to neglect for the moment. I come back to that later on. It's a small contribution. We neglect it for the moment. Then you have the phase of the next harmonic, and you have a phase due to the laser. The laser is delayed compared to the harmonics by a delay tau. So here you have a phase omega tau, and since this is an emission process, you have minus omega tau. So the signal is an interference signal as a function of the delay, and looks like this. And here in the cosine term, you have the difference of phases between the two quantum paths. So you have omega tau plus phi q, and then minus omega tau minus phi q plus tau. So you see that it's an interference signal that varies with frequency 2 omega, and that depends, and this is really what we want to measure, on the phase difference between consecutive harmonics, which is what I want to know. I want to know if the harmonics are phase-locked. I want to know how the phase vary from one harmonic to the next. And so this experiment, Pierre Agostini measured phases that were not really equal, shows a variation, but a linear variation, well-behaved, linear chirp. And and from this measurement, he could reconstruct the pulse train and obtain a pulse train with a duration of 250 attoseconds. Now I would like to present very briefly the idea of the experiment of Ferencz, which was done approximately at the same time. But before doing that, I would like to mention further progress in laser technology that was essential for Ferencz experiment, because Ferencz managed to produce isolated attosecond pulses. And for that, he needed to use very, very short laser pulses to start with. So it's really based on progress, first of all, in creating few cycle laser pulses below 10 femtosecond, using a hollow fiber compression technique, which was developed by the group of in Milan, Mauro Nisoli and co-workers, and also the technique of chirp mirrors. And also important for mastering these very, very short pulses, the control of the carrier envelope phase, which was done here in Zürich by the group of Ursula Keller. So this is the experiment performed by Ferencz. I'm not showing the first experiment, I'm showing a later experiment. We're showing much clearer that you have a single attosecond pulse. The technique is very similar to that of Pierre Agostini. It used cross-correlation between between the attosecond pulse and the laser, and also measuring the electrons that are produced. And the technique is called the streaking camera. Very simply, what you do is you ionize a gas using an attosecond pulse, and then cross-correlating with a laser pulse. If you ionize with an attosecond pulse, the electron will get some momentum, but then in presence of the laser pulse, the electron will get additional momentum, and this can be up or down depending on the when this ionization takes place relative to the laser cycle. And you get this beautiful streaking trace as you see here, and the sharper this variation of the electron energy as a function of delay is, the shorter the attosecond pulse is. And here they could measure 250 attoseconds. So I'm now coming to the last part of this talk, which is what do we do with these pulses? What are the applications? Today, this field is going into many directions, so I'm certainly not going to tell you everything what is going on. I would like to focus on two different applications. One is what we do in atomic spectroscopy, and I will also mention an industrial application. So I start by very fundamental, which is how we look at electrons in atoms using attosecond pulses. And I will really start by a simple process, which is photoionization. So the duration of this attosecond pulse matches the time scale for electron motion in valence electron motion in atoms and molecules. So the idea is to try to catch this motion. How do we do that? Well, let's look at photoionization very simply. Photoelectric effect, which was explained by Albert Einstein in 1905. I'm sure that you think about this photoelectron as a particle. Particle going to a detector, click, you measure its energy or its momentum. What we do with our attosecond techniques, I think you had lectures yesterday about the wave-particle duality. So this is, I think this fits very well. So what we're doing with our attosecond techniques is really to measure the wave property of this photoelectron. It's not only a particle, it's a wave, and we manage to measure its phase properties, its amplitude and phase, and actually even quantum property of the photoelectrons. How do we do that? Well, we use this same rabbit technique. There are also experiments using the streaking technique, but I'm going to focus on this very nice rabbit interferometric technique, which is really allows us to measure phases. So, and there are two ways to think about it. The first way is to look at non-resonant photoionization using an attosecond pulse. So you create a broad electron wave packet. And what you want to know is the group delay of this electron wave packet. In other words, you want to know the spectral phase variation of this photoelectron. You want to measure the phase as a function of energy. And we do that using this interferometric technique. The other way that you can use in a different context, and this has been done also a lot in this field, is to focus on a narrower region of the spectrum, resonant photoionization. For example, when you have a discrete state here embedded in a continuum, like a Fano resonance, and here you think that you create a small electron wave packet, but which is perturbed by the presence of this discrete state, and you want to know the phase of this wave packet. Same technique, this quantum interferometer, allowing us to access the phase of this photoelectron. So I'm not going to talk about both. I'm going to focus actually on this part, but I mentioned this just for completeness. This is also very, very interesting. So we are here. We use this rapid technique. I think I started talking about the rapid technique by mentioning that there are two terms. One, which is the phase of the light pulses, this harmonic, and then you have this contribution from the atomic ionization. And now this is the quantity I want to measure. This is the interesting quantity. So let's forget this one. How can we do that? Well, there are several ways, but one way is to actually compare different ionization process using the same light pulse, using the same harmonics, and then you can simply take the difference. And this term is the same in both cases. So you can compare this term here. And this is what we did first. Now, this is a result where we look at photoionization of neon in the N=2 shell, ionizing at the same time in the 2s shell and in the 2p shell. And we look at actually the difference in phases, we measure that in attoseconds. It's a delay difference. It's a group delay differences. And this is what we get. So this was a very high precision experiment, was actually very, very difficult to perform, but you see that we have a precision on the time measurement, which is around 20 attoseconds. So this is what we measured. What does it mean? Well, actually, what we measure here is not really this group delay due to photoionization. It's a correction due to measurement, due to the use of the infrared field, which is needed for the interferometry part. So, but this was a very important experiment just to make sure that we understand what we are doing. And what the black curve that you see is not a fit, is a theoretical calculation. So this experiment was important to really see, yes, we understand what we are doing. And now we can look at more complicated problem in photoionization. For example, argon in 3s and 3p ionization. In this case, you have Cooper minima, where the amplitude of photoionization go to 0. There are things happening which leads to different time delays. And here you have experiment performed in 2 different labs in Lund and in Saclay, showing a dip here. So this is the region of what is called the Cooper minimum in 3s ionization, and here you have 3p Cooper minimum. So here you have a very good agreement between the 2 experiments and between theory, whereas here we have a disagreement. And I'm showing this because this is an experiment we have tried to do many times since 2011, try to understand better what was happening and why there is such a huge discrepancy. At the time now, there are new experiments still showing this decrease, but there are new theory that maybe now confirm that you have a decrease. So this is where we are. We are trying to study this time delays and understand what is happening, and also try to interpret. When you have a positive delay, you can give nice interpretation with electrons which are trapped in a potential. When it's a negative time delay, it's a little bit more this kind of, you push the electron out, so it's a little bit more, it's not as intuitive, I would like to say. Just to show you that we can do better than just taking difference between 2 processes, We can also calibrate using different gases. This has been done among many labs in Zürich. But here is an experiment where we calibrate our delays relative to neon and in the same region. And this is 4D ionization in the 4D shell of xenon, showing actually two different features. This feature here is connected to the giant dipole resonance of xenon 4D shell, corresponding in the cross-section is showing a very broad resonance, and the time delays show this positive delays of the order of few tenths of attosecond. And here you have a feature which is interpreted to a spin-orbit interaction. So I'm going to stop here for this part, but there are really development. First, you can use, also detect the angular distribution of the electron to get more information. This is especially important when you have several channels for the ionization, several angular channels. And what we are trying to do is to measure not only the phase and amplitude of the photoelectrons, but its density matrix. Measuring the phase and amplitude assumes that you have a coherent wave packet, and this is not always the case. If there are loss of coherence in the sense of quantum information, you really need to do a tomography of this photoelectron, which we have recently managed to do. So now I would like to finish by mentioning one application, maybe not so much of attosecond pulses, but of the high harmonics. But it's what is, I think, extremely exciting is that this application is in the hands of industry now, the semiconductor industry. And again, to go to industry, you need more progress in laser technology. And this progress, and it's happening now, it's really thanks to the development of ytterbium lasers with a very high repetition rate and high average power and much more user-friendly, together with new post-compression techniques using a multipass cell where you have a cell phase modulation in a cell leading to a broadening, and then you have compression. And using this type of system, you can use harmonics to really control, and this is something now developed by the big company ASML in Holland. So the idea is to use the high harmonics in this range, so generated in neon gas, 7 to 17 nanometer, to control defects in computer wafers. So here you have a zoom of such a wafer containing lots of transistors, components, and now we are in this is for the next generation computer wafers with dimension of the order of 10 nanometers. And these components are packed not only in 2 dimensions, but also a little bit in the 3rd dimension, as you can see here. So the idea is to use diffraction techniques called scatterometry in order to control the wafers. And what is interesting is the fact that you have the right energy range. We are in this 7 to 17 nanometer, and you have a lot of frequencies which are needed to get the information. So we'll see how long it goes, but there are building machines now with harmonics in order to control these computer chips. So I find it very exciting. What is the next chapter in attosecond science? As I said at the beginning, it's really going to be in many directions. I think the challenge of this field is really to apply the techniques I have shown you to measure the properties of the photoelectron, to measure the dynamics of electrons in a complex system, in big molecules, or in condensed matter physics. I think that's very important, and I think it's done quite a lot in Zürich among many labs. Industrial application, I have mentioned and briefly mentioned this direction towards quantum information. Now I have talked about attosecond sources via high-order harmonic generation. They are in the XUV range, although there are ideas to extend it towards X-ray using mid-infrared radiation. In general, low energy per pulse in the nanojoule, very often in a train, although it's possible to obtain single pulses. I think there is very, very interesting new sources thanks to the X-ray free electron lasers, and was very happy this morning to visit the Swiss FEL light source, and they only talk to me about attosecond pulses, so they know how to do it. So these are in the X-ray range. They are often isolated and much higher energy per pulse. We are in the microjoule range, and there is a huge progress the last 2 years. So I think a large part of this next chapter in attosecond science is going to be using these free electron lasers. So with that, I would like to conclude. I think now I'm talking to the young people here. If you are happen to be a little bit at the right place at the right time, you might end up here, which is in Stockholm on the 10th of December. It was 2023, and it's a very, very nice and symbolic ceremony. With you have Alfred Nobel here. These are people from the academy. You have the royal family here, and these are the Nobel laureates. This is myself here. And maybe you get a medal from His Majesty the King of Sweden. And after this ceremony, which is in the concert hall in Stockholm, you have the Nobel banquet, which is in the city hall. This is a huge building, and you have 1,300 guests at this banquet. And this is me. And for a French person being educated with the French Republic and all of that, sitting for hours close to the King of Sweden was a real experience. So I would like to thank many people. Of course, this research has been done by many, many people over the years, and this is just a photo of my group. They are not dressed up like this, usually. They are actually celebrating this Nobel event in Lund on the 10th of December last year. And of course, very nice, these are the senior people working with me since many years. Of course, we need organization to finance this research. This is the Science Swedish Council, ERC, and the Wallenberg Foundation. And finally, I would like to thank you for your attention, and the Swiss Physical Society and Swiss Society for Photon Science for organizing this meeting. Thank you.
Thank you very much. I think we have some time for a few questions. So please use the microphone because we're recording this.
So to us young PhD students in physics in the audience, what mindset and what methods would you recommend to us?
So, sorry, what mindset and method what?
And methods. would you recommend to us?
Yeah, I mean, I would say the most important two things. One is passion. You need to like what you are doing and think it's fantastic, which is what I did from this day we saw harmonics in the first place. Was really for me, I had no idea that this could lead to a Nobel Prize, but I was simply fascinated by this process and wanted to know more. And the second thing you need is persistence and not give up, because I mean research, career in research always ups and downs, and of course there were times where it was very tough. At the end of the 90s, we had not a clue how we could measure attosecond pulse. At least there was my case, and it was not clear at all that this would lead in. So you need a little bit of obstinacy and persistence. So that's my answer.
More questions?
Thank you very much for this lovely talk. I was simply wondering if people try to expand this plateau to even higher orders and try to generate even shorter pulses, like below attosecond. Is it possible, or is there a limit at some point?
Yes, it's possible. You use mid-infrared radiation, and then you get very long trajectories. So the electron can get a lot of kinetic energy, and this leads to very long plateaus. Unfortunately, the efficiency is even lower. But so now you get very long plateaus. And I think the shortest pulse that has been measured is about 43 attosecond. The difficulty then is to make sure that all of these harmonics are approximately synchronized, or not to. So that's the difficulty, is to make them, not to, approximately phase locked. This is what is. I think this is what is preventing to make even shorter pulses. There is bandwidth, but make shorter pulses is difficult.
We have one more question.
Thanks a lot for the talk. I was wondering, do you think, is that theoretically a kind of limit to the duration of the pulse, like linked to Heisenberg, as we have time energy that is limited? Is there this kind of limit, or we maybe can be able to go as small time as possible?
I think that we are not violating Heisenberg principle, and we are far from it. I can answer several ways your question. First of all, of course, you get very short pulse, you need a broad bandwidth. And then, for example, the measurement that we did, where we have a very good precision of 20 attosecond, how did we get that? Are we violating Heisenberg principle by having this precision? No, because we are using, we repeat, we have short attosecond light pulse, but we repeat the process. We have a long train. So this is how we, I would say, circumvent Heisenberg principle.
And do you think that we can go even in the shorter pulses?
Shorter, I think you can, but I think you can get even shorter precision if you have a very, very stable interferometer. So, and use this interferometric technique.
More questions?
Another one top.
Thank you for the talk. It was really great. When you were talking about the ionization with the 3p and 3s in argon, you mentioned there was some theory that could explain it. Could you give like a brief introduction or something?
Yes, I think what this theory. It's not me, so but what is this new theory adding now? So the theory doing this is based on the random phase approximation with exchange, so it's very good results. But now they add more correlation effects and actually the shake-up processes. So doing that, it seems that now we have a theory curve actually going down. The interpretation of this is still a bit unclear, but this is going on, and I wanted to show that, I mean, research takes time, and we again, it's important to be persistent. Yeah.
I suggest that we take one last question there from the back.
You've had this amazing career at the forefront of a relatively new field in physics. If you had to choose a new PhD topic today in 2024, which field do you think could see the same kind of great developments in the near future?
I think I would. I think this field is fantastic, and you have the lasers are improving every day, and they are, and you. This field is completely open. Really, the next chapter is to do really look at electron dynamics in complex materials. There is a lot to do, and then you can use different. There are many things I didn't talk about. You can use different states of polarization. You can use lots of type of detector. There are so many things you can do. So I would say, attosecond science is a good